Hello everyone, and let's do some more example of indefinite integrals by substitution. So next example, we have to integrate 3 sine over the square root of 1 plus cos of x dx. Again, this is not a basic integral, so we're going to try to do a change of variable to make this as simple as possible. So here, quick inspection, we have a denominator, which is the square root of 1 plus cos of x. And we have also something inside the square root, which is like 1 plus cos of x. Derivative of 1 plus cos is minus sine. We have minus sine up there. So this is going to be my best try. So let's use u equal to 1 plus cos of x. Then you compute its derivative right away. So the derivative of u with respect to x is minus sine of x. Then you isolate dx, so you just make the swap here. So you get du over minus 1 sine of x is equal to dx. All right, so 1 plus cos will be replaced by u. Dx will be replaced by du over minus sine. So here we go. Now we get the integral of 3 sine, so this is untouched initially by your creepy ends, over the square root of u, and dx is now du over minus sine of x. So now let's cancel stuff, and if the U substitution was done properly, every single term that depends on x should simplify, and here it works. So we see sine of x canceling perfectly. We can take the coefficient out, so the 3 over minus 1, I'll take it outside as minus 3, so this is equal to minus 3. The square root of u, this is u to the power 1/2. I'm going to bring it up as u to the power minus 1/2, so we have the integral of u to the power minus 1/2 du. Now we have a basic integral with respect to u. I'm going to use a power rule, so you raise the power by 1. So this is equal to minus 3. I like to put things in bracket so that there's no confusion, that everything is multiplied. So here we get u to the power minus 1/2 plus 1. If you're comfortable in your skin, you can write 1/2 right away, divided by minus 1/2 plus 1 plus c. So once the integration is done, you have to make sure that your answer is a family of functions. So you write your plus c. Now if you replace u by its original formula, u is 1 plus cos of x. So here we get minus 3, 1 plus cos of x, minus 1/2 plus 1, that's 1/2, divided by 1/2 plus c. If you want to clean this up a bit, divided by 1/2 is like multiplication by 2, so you get minus 6. Power 1/2 is like a square root, so you get the square root of, okay, so square root of 1 plus cos of x plus c. And that's your answer. Next example. All right, next example. We want to compute the integral of ex times sine of 3ex minus 1 dx. So again, first remark, this is not a basic integral. We have a bunch of product. We also have a function inside a function. Here, when we have something inside a function, like here 3ex minus 1, that equation is inside the sine function. So let's try to use this as our u variable. So let u be equal to 3ex minus 1. As soon as you make your choice, you compute the derivative. So you get du over dx is equal to 3ex minus 0. Then you isolate dx, so you get du over 3ex is equal to dx. So I have a formula for dx too now, which is du over 3ex. So now our integral becomes, with this u substitution, the integral of ex, unchanged, sine of u, like all the inside of sine is simplified to this brand new variable, and then dx is du over 3ex. And now this is the part where you hope your substitution is done well. So it will be a good substitution if everything simplifies algebraically. So you see the ex cancel the ex here. So you're left with 1/3 the integral of sine of u du. And the integral of sine of u du with respect to u, this is a basic integral. The integral of sine, or one integral of sine, is minus cos. So you get 1/3 times minus cos of u plus c. And then the last bit is to simply replace u by its original equation. So you get minus 1/3, if you combine the coefficient, cos of 3ex minus 1 plus c. And that's your final answer for that example. All right, next. All right, now we want to compute the integral of secant squared of square root of x, all of that over square root of x dx. Again, not a basic integral. We have a quotient to things. We have something inside secant squared. So here, if we look at the common strategies using either the denominator or the inside of the secant squared, we have the square root function. And here between the two, because I know that the derivative of square root of x is 1 over 2 square root of x, which I have in this expression, I'm going to use the inside of the secant squared. Even if it's the same formula, be careful. I'm just going to use the inside of the secant squared for my u. So u is going to be the square root of x. Then du over dx, the derivative of the square root of x is 1 over 2 square root of x. Well, it's x to the power 1/2. You use a power rule, you get 1/2 x to the power minus 1/2, which simplifies to 1 over 2 root of x. But my advice, you should really learn by heart that the derivative of square root of x is 1 over 2 square root of x. So if I isolate dx here, you get 2 root of x du is equal to dx. So now I have a formula for dx also. And the formula is 2 root of x du. So now this integral becomes the following. I have the integral of secant squared u. So be careful, I only use the inside of the square root as my u initially. So dx is now 2 root of x du. And now this is all over root of x. And now you see this nice feeling, this root of x. And root of x simplifies perfectly. So I can put the 2 outside. So you get 2, the integral of secant squared of u du. Look at this integral with respect to u. This is a basic integral. The integral of secant squared is tan. So you get 2 tan of u plus c, where u is the square root of x plus c. And that's my final answer. Yay! All right, next example. One of my favorite one. Okay, so the integral of ln of x over x dx. Again, quotient of two functions, no quotient rule sadly in integration. So what can I do if I look at the denominator? X is u, so you're not going to do that. We have a ln function, inside is just x. We're not going to replace x by u. This is just a waste of time. But if we use u as ln of x, I know the derivative of ln of x is 1 over x, and even if you can't really see it here, 1 over x is part of the formula. Maybe sometimes it's useful to rewrite this as the integral of ln of x, and when you divide by x, it's the same thing as multiplying by 1 over x dx. So this is the exact same equation, but sometimes it's easier to see that, oh, I have a 1 over x in that equation, which is the derivative of ln of x. So if I use this general philosophy of choosing a chunk of your equation that is such that its derivative is there up to a coefficient, my inspiration begins. So here we go. So let's use u as ln of x, then du over dx is 1 over x. If I isolate dx here, I get du times x. Times x is equal to dx. So I have a formula for dx. I have a formula for u. So let's do some substitution. So here we go. So this integral will become, so this is equal to the integral of u times 1 over x, and the dx is x du. And this question, of course, everything simplifies perfectly. 1 over x times x cancels to 1. So you're down to simply having this pure integral, the integral of u du. Remember, the integral of u is u to the power 1. So you get u squared over 2 plus c using the power rule, where u is ln of x. So you get ln of x squared over 2 plus c. That's it. That's all for that example. Now, let's integrate cos of 1 plus 1 over x squared dx. This one is very similar as the previous one, where you have this denominator being x squared. If you try to use x squared as u, the derivative of x squared is 2x, or a multiple of x, which you don't have in this expression. But inside the cosine, there's 1 plus 1 over x, and 1 over x, when you compute its derivative, it's minus 1 over x squared, and you have here minus 1 over x squared up to a multiple. And maybe just to see it clearly, this integral is the same as the integral of cos of 1 plus 1 over x times 1 over x squared dx. And here, this helps to build the intuition that the inside of cosine, its derivative is out there next to dx up to a multiple. So let's use this as the U substitution. So let's use u is equal to 1 plus 1 over x. Then du is going to be minus 1 over x squared. Sorry, du over dx. Hello, du over dx. So if you isolate dx here, you get minus x squared du is equal to dx. So we have a formula for dx. So we know that u is going to be replacing 1 plus x, and dx is going to be replaced by minus 1 x squared du. So if you apply your substitution, this integral becomes the integral of cos of u times 1 over x squared, and then dx is minus 1 x squared du. This is where the magic begins. X squared over x squared, bye-bye là. You can put the minus 1 outside. I like to put the coefficients outside. It's up to you, of course. Up to you. Sorry. So here we have the integral of cos of u du. A nice basic integral. The integral of cos is sine, so you get minus sine of u plus c, where u, at the end of the day, is turned back into 1 plus 1 over x plus c. And that's it. That's all for all those nice examples of U substitution. Bye-bye.